All right. Feels nice to multiply binomials, doesn't it? All right, Henry, x plus 1 to the 0. That was a nice one, wasn't it? Connor, x plus 1 to the first. Okay. X plus 1 the quantity squared. What do you have, Jen? Okay. Then you use that for x plus 1 the quantity cubed. Amanda, what do you have?
I have x cubed plus 3x squared.
Okay. And then, what do we have for x plus 1 the quantity to the fourth? Molly, did you get that one?
Not yet.
Not yet. Still working on it? Okay. Kelsey, did you get that? What did you get?
I have x to the fourth plus 4x cubed plus 6x squared plus 4x.
Molly, are those sounding okay?
Yeah.
Yeah? Okay. All right. I want you to look at this. I want you to discuss in your pod any pattern that you see. 1, 2, 3, go. Look at those coefficients. All right, Darby, what pattern is this following?
It's my homeboy, Pascal's triangle.
Pascal's triangle. Do you remember this?
Oh, yeah.
Okay. Darby clearly remembers it. Do the rest of us? Yes. Okay, let's talk about the pattern of Pascal's triangle. We start with a 1. And then 1, 1. Then notice 1, 2, 1. We take these ones, we add them together to get this 2. All right? Then for the next row, we have 1. If we add 1 and 2, we get this 3. If we add 2 and 1, we get this 3. And then a 1. Next row, we take 1 and 3 to get 4. We take 3 and 3 to get 6. We take 3 and 1 to get 4. Do you see the pattern? Isn't it beautiful?
Gorgeous.
And it's an aesthetically pleasing shape for this time of year.
We draw some.
You draw what?
Oh, you did the ETC is liquid.
Wonderful.
Okay. Now, what do these numbers represent? These are the coefficients when we expand x plus y to the n power. Okay? Pascal's triangle represents the coefficients for each term when we expand out a binomial. Okay. Now, our triangle does start with what I call the 0 row, and then the first row, then the second row. So if we look for the expansion of a cubic, then we can look at this third row right here. 1, 3, 3, 1 are those coefficients. If we want the expansion of a 5th degree binomial, then we can look at these numbers right here in the 5th row. Okay, this number right here will tell you which row it is. Okay. Now, if I ask you for like x plus y to the 12th power, probably not going to do that. But if I did, do you really want to sit there and write out 12 rows of Pascal's triangle to figure out your coefficients? Okay, you do not have to multiply binomials over and over and over and over again anymore. We can use this shortcut right here. If we expand a binomial to raise to a power, instead of multiplying binomial times binomial, and then that times a binomial, and then that times a binomial, we can do this. Okay. Some of you got kind of frustrated having to do x plus 1 to the 4th power, right? Takes a lot of work. We can cut our time in half, maybe even more, with the binomial theorem. Gabe, what does that C stand for in NCR? Does it stand for coefficient? Amanda disagrees. Amanda, what do you think it stands for? Okay. What's another word for that? Combination. Okay. This is the combination, n combinations of R. Okay. Now, we're taking a sum of a sequence. So we plug in 0 for R. Then we plug in 1, then we plug in 2, then we plug in 3. And when we reach this number up here, then we know that we are done. Okay. So if we're expanding something raised to the 2nd power, we're going to have 3 terms. If we raise something to the 5th power, we're going to have 6 terms. Mrs. Holman, you just told us that the coefficients of a binomial are Pascal's triangle. But here, I'm telling you that they're this. Guess what? Pascal's triangle is the same as when we list out these combinations. Isn't that cool?
Sure you got the pattern.
Okay, so this row right here, 1, 3, 3, 1, is the same thing as 3 combinations of 0, 3 combinations of 1, 3 combinations of 2, 3 combinations of 3. Notice how it's that 3 row, and so all of these are 3 combinations of something, and we start with 0 all the way up until we get to 3. And then the next row is 4 combinations of something, 4 combinations of 0, all the way until we get to 4 combinations of 4. Okay? So when we get back from lunch, we are going to talk about how to apply this formula to expand a binomial raised to the power so that we actually don't have to do any quote-unquote foiling. Okay? Please.
This is when I think about like 6th grade me. And like, oh my goodness.
Please write down this example. Now, you are more than welcome to write out Pascal's triangle and figure out what the row is with the 1 and the 4 for this one. Or we can just use, I'll be right back, this right here to write out each term. So, when we use that summation, we have the NCR, and then we have the x to the power and the y to the power. So the first term and the second term in your binomial both to the power. So, we are going to start with 4 combinations of 0. Whatever this number is, that's what goes with your combinations, and we're always going to begin at 0. Okay? Then we are going to take this first term in the binomial. That will always be raised to the n power, whatever this number is for the first term. And then we take the second term. In this case, it's -3 because we're subtracting 3. And that is going to be raised to the 0 power. Okay? You will always begin with the first term raised to the n power, the second term raised to the 0 power. Okay? That's your first term. Your second term. Now what we're going to do is we're just going to increase this number right here. See where I'm pointing? This number right here by 1. So 4 combinations of 1. 2x will now go to the third power. And -3 will then go to the 1 power. So your first term is going to decrease with the exponents, while your second term is going to increase with their exponents. Then we will move on to 4 combinations of 2. 2x will now be raised to the 2 power and -3 to the 2 power. We decreased the first term's power, we increased the second one. After 4 combinations of 2 comes 4 combinations of 3. 2x is now to the first power and -3 to the third. And we know we are on the last term now because we have 4 combinations of 4. 2x is then to the 0 power and -3 to the fourth. Now before you begin multiplying things out, I want you to notice a couple things about this pattern. This number right here that I'm highlighting in, oops, not that one. The number that I'm highlighting in red, what does that match in each of the terms? Okay, the exponent on that second piece, all right? So whatever the term is here, the second term in the binomial, its power will always match that combination number. Okay? All right, so you can either remember that Pascal's triangle is 1, 4, 6, 4, 1, or you can do the calculations in your calculator. 4 combinations of 0 is 1. 2x to the fourth is 16x to the fourth, and -3 to the 0 is 1. So our first term is 16x to the fourth. All right, then you can calculate 4 combinations of 1 is 4. 2x cubed, notice how the 2 and the x are being cubed, excuse me, is 8x cubed. I had a moment of paying attention. And then -3 to the first is -3. So our second term is -96x cubed. Our next term. What is 4 combinations of 2? 6. 2x, the quantity squared, is the same as 4x squared. And -3, the quantity squared, is a positive 9. So our third term is what? What, did you say something? Is 216x squared. Four combinations of 3 is 3. 2x to the first is 2x. And -3 cubed is -27. So our fourth term is -216x. And then finally, our last term, 4 combinations of 4 is 1. 2x to the 0 is 1, and negative 3 to the 4th power is a positive 81. Yes.
What's the second to last term?
This one right here.
Yeah. So,
4 combinations of 3s.
yeah.
4. Thank you. It's still 216, isn't it?
Yeah.
Okay. Okay, having to take 2x minus 3 times 2x minus 3 times 2x minus 3 times 2x minus 3. I know we can all do that, but it is time consuming and it is very easy to make a simple arithmetic mistake. Mismultiplying, misadding, losing some sort of sign somewhere, okay? The organization is sometimes where we get tripped up. Here, yes, it takes a little bit of time to write everything out, but it's the calculations are much simpler, okay? And it's still going to save us some time. Any questions about any of those terms up there? On to example 2. So x squared is our first term, and positive 4 is our second term. Like I said, you can either remember Pascal's triangle, or you can just do all of these combinations. So, since this is being raised to the 3rd power, we're going to start with 3 combinations of 0. The first term in our binomial is x squared. Amanda, what are we going to raise x squared to? To the 3rd power, because that is n. And then positive 4 is the second term. What power do we raise that to, Kanan? 4. The amount of very first term.
0.
Good. Okay. Then we're going to move to 3 combinations of 1. X squared gets raised to what power, Tori?
2.
Good. And 4 gets raised to what power, Marissa?
1.
Good. Then we have 3 combinations of 2 times x squared, everybody, to the, okay, let's try that again. X squared gets raised to what power? And 4 to the, you guys really need some enthusiasm today. And then we have 3 combinations of 3, x squared to the 0, and 4 cubed. All right, Zach, what's 3 combinations of 0?
1.
So we have 1 times x to the 6th times 1. Our first term is x to the 6th. Three combinations of 1. What is it, Molly?
3.
Yep. X squared squared is x to the 4th. 4 to the 1st is 4. So our second term is 12x to the 4th. Three combinations of 2 is also 3. X squared times 16. 16 times 3 is what? Okay, so then 3 combinations of 3 is 1, x squared to the 0 is 1, and then 4 cubed is 64. So our last term is 64. Coming back. Bring back some memories from last year. Yes? Yes. Good. Now, this is what I want you to notice. If I'm looking for the third term in this, is the third term 3 combinations of 3? No. Our first term begins with 3 combinations of 0. So our third term is going to be 3 combinations of 2. And then so on and so forth. Okay? I am not going to give you anything higher than like a 6 power to multiply all the way out with the binomial theorem. I'm not going to give you like x plus y to the 12th, okay? However, I could ask you for a particular term from a binomial expansion. So go ahead and write this example down. I want the 6th term from a plus 2b raised to the 8th. Okay, please turn to your neighbor and decide how you think we should set up the 6th term for this expansion. All right, everyone back up here together. Ryan, what did you and your neighbor decide? Did you write anything down? Okay, let me ask you this. If we're starting with the 6th term, then we have 8 combinations of what?
Oh, no.
Okay, 8 combinations of 5, so we can at least start there. All right? Then we know that we need a to a power and we need 2b to a power. Okay? Now, this number is going to match which exponent? The first or the second? Okay? So we know this has to be a 5. And if this is an 8, this is a 5, what does this exponent have to be? Yep. Not sure if we've officially talked about it. I'm sure most of us have made this observation, but these two exponents will always add to that end value. Okay? All right, so this is our setup for the 6th term. Okay? Write down the combination, write down each piece, and then based off of this number, figure out your exponents. Okay? So what is 8 combinations of 5?
56.
56. So we have 56 times a cubed. Remember, 2b is being raised to the 5th power. So that means this is 32b to the 5th. I'm not going to multiply that in my head. What is it? 792 a cubed b to the 5th. Okay. You and your partner next to you, if there's 3 at your table, then everyone at your table. Try and set up this problem. Don't multiply anything out, just do the basic setup of the whatever combinations of whatever, blah, blah, blah. If I'm asking for the coefficient of a to the 6th, b to the 5th, how do you think we should set this up? There's not a lot of talking going on right now. It makes me a little bit nervous. It's a partner task, not an individual task. Just set it up. I don't want you to multiply anything together until you know that it's for sure correct. All right, Miss Sarah, can you tell me how you and your neighbor set it up? Raise to the what? 5. Okay, can you talk through the process of how you came to this decision? Okay, good. So since this was a to the 6th, b to the 5th, she knew that 3a needed to be raised to the 6th, negative 2b needed to be raised to the 5th power. And then since this was an 11, we had 11 combinations of something, and it's a 5 because it needs to match this exponent right here. So 11 combinations of 5. Help me out. For what?
66.
416?
62.
Okay. We should talk a little more clearly. 3 to the 6th. And then negative 2 to the 5th would be negative 32. What do you get when you multiply 462, 729, and negative 32?
Negative 10,736.
Okay. This is our term. What did it ask for? The coefficient. Okay? So read the directions, and if you find the term, just use your eraser and erase out the variables. Okay? All right, thumbs up, thumbs middle, thumbs down. How do you feel? Okay. Your homework, I would really just ignore that. I would just look at your gold sheet. It'll make a little bit more sense.